In the last section, we continued to talk a little bit about images, but we're still surprisingly light on some of the details around exactly what a container is. So in this section, I'm going to give you a behind-the-scenes look at what a container is and how it is created on your machine. Now, to understand a container, you first need to have a little bit of background on exactly how your operating system runs on your computer. So I'm going to first give you a quick overview of your operating system. Okay, so this is a quick overview of the operating system on your computer. Most operating systems have something called a kernel. This kernel is a running software process, governed access between all the programs that are running on your computer and all the physical hardware that is connected to your computer as well. So up here at the top of this diagram, we have different programs that your computer is running, such as Chrome or Terminal, Spotify, or Node.js. If you've ever made use of Node.js before and you've written a file to the hard drive, it's technically not Node.js that is speaking directly to the physical device. Instead, Node.js says to your kernel, hey, I want to write a file to the hard drive. The kernel then takes that information and eventually persists it to the hard disk. So the kernel is always kind of this intermediate layer that governs access between these programs and your actual hard drive. The other important thing to understand here is that these running programs interact with the kernel through things called system calls. These are essentially like function invocations. The kernel exposes different endpoints to say, hey, if you want to write a file to the hard drive, call this endpoint or this function right here. It takes some amount of information, and then that information will be eventually written to the hard disk or memory or whatever else is required. Now, thinking about this entire system right here, I want to pose a kind of hypothetical situation to you. I want you to imagine for just a second that you and I have two programs running on our computer. Maybe one of them is Chrome, like Chrome the web browser, and the other is Node.js, the JavaScript server-side runtime. I want you to imagine that we're in a crazy world where Chrome, in order to work properly, has to have Python version 2 installed, and Node.js has to have version 3 installed. However, on our hard disk, we only have access to Python version 2. And for whatever crazy reason, we are not allowed to have two identical installations of Python at the same time. So as it stands right now, Chrome would work properly because it has access to version 2, but Node.js would not because we do not have a version or a copy of Python version 3. Again, this is a completely make-believe situation. I just want you to kind of consider this for a second, because this is kind of leading into what a container is. So how could we solve this issue? Well, one way to do it would be to make use of an operating system feature known as namespacing. With namespacing, we can look at all of the different hardware resources connected to our computer, and we can essentially segment out portions of those resources. So we could create a segment of our hard disk specifically dedicated to housing Python version 2. And we could make a second segment specifically dedicated to housing Python version 3. Then, to make sure that Chrome has access to this segment over here and Node.js has access to this segment over here, anytime that either of them issues a system call to read information off the hard drive, the kernel will look at that incoming system call and try to figure out which process it is coming from. So the kernel could say, okay, if Chrome is trying to read some information off the hard drive, I'm going to direct that call over to this little segment of the hard disk over here, the segment that has Python version 2. And Node.js, anytime that makes a system call to read the hard drive, the kernel can redirect that over to this segment for Python version 3. And so by making use of this kind of namespacing or segmenting feature, we can have the ability to make sure that Chrome and Node.js are able to work on the same machine. Now, again, in reality, neither of these actually need an installation of Python. This is just a quick example. So this entire process of kind of segmenting a hardware resource based on the process that is asking for it is known as namespacing. With namespacing, we are allowed to isolate resources per process or a group of processes. And we're essentially saying that anytime this particular process asks for a resource, we're going to direct it to this one little specific area of the given piece of hardware. Now, namespacing is not only used for hardware, it can be also used for software elements as well. So for example, we can namespace a process to restrict the area of a hard drive that is available, or the network devices that are available, or the ability to talk to other processes, or the ability to see other processes. These are all things we can use namespacing for to essentially limit the resources or kind of redirect requests for resource from a particular process. Very closely related to this idea of namespacing is another feature called control groups. A control group can be used to limit the amount of resources that a particular process can use. So namespacing is for saying, hey, this area of the hard drive is for this process. A control group can be used to limit the amount of memory that a process can use, the amount of CPU, the amount of hard drive input-output, and the amount of network bandwidth as well. So these two features put together can be used to really kind of isolate a single process and limit the amount of resources it can talk to and the amount of bandwidth, essentially, that it can make use of. Now, as you might imagine, this entire kind of little section right here, this entire vertical of a running process, plus this little segment of a resource that it can talk to, is what we refer to as a container. And so when people say, oh yeah, I have a Docker container, you really should not think of these as being like a physical construct that exists inside of your computer. Instead, a container is really a process or a set of processes that have a grouping of resources specifically assigned to it. And so this is a diagram that we're going to be looking at quite a bit anytime that we think about a container. We've got some running process that sends a system call to a kernel. The kernel is going to look at that incoming system call and direct it to a very specific portion of the hard drive, the RAM, CPU, or whatever else it might need. And a portion of each of these resources is made available to that singular process. Now, the last question you might have here is, okay, well, I get what a container is, but with that in mind, what is the real relation between one of those containers, or that kind of singular process and group resources, to an image? How does that single file eventually create this container? Well, that's a good question. One more quick diagram. Anytime that we talk about an image, we're really talking about a file system snapshot. So this is essentially kind of like a copy-paste of a very specific set of directories or files. So we might have an image that contains just Chrome and Python. An image will also contain a specific startup command. So here's what happens behind the scenes when we take an image and turn it into a container. First off, the kernel is going to isolate a little section of the hard drive and make it available to just this container. And so we can kind of imagine that after that little subset is created, the file snapshot inside the image is taken and placed into that little segment of the hard drive. And so now inside of this very specific grouping of resources, we've got a little section of the hard drive that has just Chrome and Python installed, and essentially nothing else. The startup command is then executed, which we can kind of imagine in this case is like, startup Chrome, just run Chrome for me. And so Chrome is invoked, we create a new instance of that process, and that created process is then isolated to this set of resources inside the container. So that's pretty much it. That is the relationship between a container and an image, and it's how an image is eventually taken and turned into a running container. Now, there's still a tremendous amount more to learn about containers and images, so let's take a quick break and continue in the next section.